Good morning. My name's Kirshman. I'm from Applied Wave Research, and today we're going to talk about RF link prediction, a new and novel approach. So traditionally, engineers tend to use an Excel spreadsheet to do calculations such as cascaded noise figure, P1 dB compression point, or third order intercept point of an RF link. The disadvantages of going about the traditional method of using an Excel spreadsheet is typically they do not account for a mismatch between components or a noise at the image frequency. And traditionally, you cannot do yield or optimization with an Excel spreadsheet. So the novel approach is to use a system tool that is designed for this type of analysis. AWR provides a budget tool, RFB, or RF budget analysis, and you start from an Excel interface where you'll define the components, whether it be a mixer, an amplifier. The components can be file-based or circuit-based. And from there on, you go to define the measurements. This common measurements such as cascaded noise figure, cascaded P1 dB of the circuit. And from this point of view, you get greater insight onto what's happening. So here we'll look at a typical example. We have a link over here where we start with a CW tone, an amplifier, followed by a filter, an attenuator, and then a conversion. We look at the LO path. We have a CW tone, an attenuator, a model that's representing a cable, and then amplification, and we go directly into the LO. We do the analysis in our system tool, Visual System Simulator, and we note a large difference in the cascaded noise figure. A traditional Excel spreadsheet gives us roughly 4 dB of noise figure, and VSS results in about 11 dB. So the question is, what's happening to this link? I did all the math correctly. I followed the math according to the textbook. I entered the math into the Excel spreadsheet, and I expect to get 4 dB. I built the design, I made the analysis, and I'm not getting 4 dB. So we ponder, and we think, and we blame the tool. The tool is wrong. It's always the tool, or I didn't read the help, and I don't know how to use the tool. But then I think, and I say, wow, this tool has lots of measurements. Let's do a further analysis of the yellow link. The analysis that we do here is we make the power spectral density measurement. At the very beginning of the link, that's thermal noise, minus 174 dBm hertz. But gosh darn, we got that amplifier in there. What's happening? Well, there's gain in the amplifier. What does that do to thermal noise? Well, it brings it up. The power spectral density measurement indicates that. And what happens when the power spectral density of that level runs through the LO path? The noise figure goes up. So the equations don't show me that. I followed the book. I did everything according to the book. The tool gave me greater insight on the link. So then what do? We place the filter. Et voila. We go down to minus 174 dBm hertz, the power spectral density running into the LO of the mixer, and we get the expected measurement. A typical example, easy to understand. Let's look at another example. I can replace the behavioral filter with an actual circuit implementation. I do the analysis. I look at the S parameters, specifically the S21 and the S11 here. And I'm going to go down to the circuit level, and I'm going to say, what happens if I switch a particular component level? What happens if I tune on the inductance of one of the inductors in this filter? And as I change the S11 response, or the reflection, once again, I can see the impact on noise figure. So now we have two cases where we have differentiated from the typical Excel spreadsheet. One, power spectral density running through the LO path, causing noise figure to go up, a higher power spectral density than thermal. Another instance here where we're tuning or optimizing on an inductance value, changing the S11, hence changing the noise figure. Let's look at a little more complicated example. The goal here is to measure the ratio of the third order intermodulation product to the carrier, IM3 DBC. We're going to go through the process of using a typical spreadsheet, and then we're going to build the system in Visual System Simulator. And once again, we see that the tool doesn't agree with standard measurements. The answer, we'll find out why, but the question is the tool wrong? Why doesn't the tool give me the same numbers as the Excel spreadsheet? The Excel spreadsheet for the ratio is roughly 31, and VSS is calculating roughly 40. Why is there a difference? Let's look. We'll measure the third order intermodulation product at the output of the second mixer, and we'll compare it to the Excel spreadsheet. VSS, we have the intermodulation product as minus 92 dBm. The spreadsheet is calculating minus 97 dBm. We're just measuring the ratio of that tone to the third order intermodulation product. To get to minus 97 dBm, we have here the previous value for the third order intermodulation product is minus 101, and we've added minus 105 dBm and got to minus 97 dBm. Okay, VSS is calculating minus 92 dBm. So we think and wonder what's going on. In VSS, we have a tool called the RF Inspector. It's a spur analysis tool. It allows me to understand the contributions to that particular spur. What caused that spur to be at that particular value? And we see over here in VSS that the font's too small on the slides. It's early in the morning, I can't even read the numbers, but we have an indication over here there's something contributing to that third order intermodulation product to make it higher than expected. Something is folding in to the third order intermodulation frequency. Note, I don't have any frequencies labeled, but there's a combination of tone A, tone B, and C in the index of 1 on the first LO. So the combination of A minus B minus C plus the LO is causing that value, the minus 105 dBm, to be minus 99 dBm. That's what VSS calculated. Something folded over into that third order intermodulation product. So voltage combined, minus 95.5 dBm plus minus 101 dBm is minus 92 dBm. So what's coming into that mixer? Right over here, okay? At that point, we got tone C, A, B, and C combined with the LO. That value fell into the third order intermodulation product. So what do we got to do? How do we get rid of the combination of tone C, A, and B in the LO? Math doesn't tell us what to do. The spur analysis told us what to do. It said, why don't we place a filter to eliminate unwanted tones? We put a filter at that point to eliminate any of the tones, A, B, and C. We can't eliminate the LO, but once we suppress one of those tones, A, B, or C, we can get exactly what the spreadsheet says. minus 101 from the previous, and we get in VSS minus 106. If I'm really worried about that, I can dive into the minus 106 dBm and see what contributed to that to make a difference in minus 105. Put a filter. I chose to reduce one of the tones, or actually two here. We make the measurement, okay, and then we get the same results as the Excel spreadsheet. So using this new approach, it's not new, it's just newer than an Excel spreadsheet. We get a richer set of models that can be used than a typical Excel spreadsheet. We get real-world effects that are accounted for in the calculations. We can do spur analysis, optimization analysis, and yield analysis and such tools. And that's the story in a nutshell.